Continuing on, we want to start talking about percent yield. So everything we've talked about so far has been in basically an ideal setting. These stoichiometry calculations are giving you the numbers that would correspond to perfect reactions. In real life, things never go perfectly. You mix reactants together and they just don't react. Or maybe you put reactants together, but there's something else in there, like say air or water, and they react with that instead, right? You have a goal that these two compounds are going to react together, but they don't behave well. Or maybe you make some product and then that product does something else, right? It reacts with air or water. Or sometimes you make product, but you can't collect it. Right? You literally drop it out of your beaker, or it gets stuck in a filter, or it's dirty, or something like that you can't use it. And so just because you run a chemical reaction, or just because you do a stoichiometry calculation, doesn't mean when you run that chemical reaction, you're going to get the same mass that you predicted in your calculation. So what we want to do is talk a little bit about how we characterize the efficiency associated with this. So theoretical yield, so we're going to use this word yield quite a bit. Yield means mass of product. So theoretical yield is the mass of product that theoretically could form. These are the answers we've seen from stoichiometry. So as the name implies, these only exist in theory. That also means whenever we need a theoretical yield, we can do that calculation ourselves. So for example, that silver copper problem we did, that was one you can just, that is it. If you wanted that theoretical yield, we've already calculated it. You do not need to do an experiment or anything like that. You can always get a theoretical yield yourself. These numbers correspond to perfect efficiency. And what perfect efficiency means in this case is that all of these silver atoms react with all of these copper atoms, and you perfectly convert all of them into product. So every single atom has gone into the product in a usable form. So you have a perfect little nugget of copper that has come out. When you watch this week's lab, want to note, you can see all the levels of imperfection that I go through. So actual yield is the mass of product actually formed. So actual yield reflects reality. This is what you obtained in real life. So if you did this reaction, 15.6 grams of silver was the number that we chose. So say you put in 15.6 grams right here. Theoretically, you can make 4.6 grams of copper. You can never make more than that. The actual yield will always be less than or equal to the theoretical yield. So the theoretical yield is your ceiling. So that is the highest you can potentially do. The actual yield will always be lower than that. It can never be higher, because being higher than that implies you have created new atoms, right? You've created extra atoms, and that violates our balancing, that law of conservation of mass that we talked about. So actual yield is almost always a bit lower than theoretical yield, but definitely never higher than the theoretical yield. We put these two numbers together in what we call the percent yield. So that's actual yield as a percentage of theoretical yield. The goal of percent yield is it measures efficiency. And so the idea of measuring this efficiency is that sometimes your yields could be on the orders of either milligrams or tons. And so converting to a percent yield gives you a consistent metric to use to kind of identify how good you have done at performing some sort of reaction, how close you were to, or how efficient you were. And related to the idea that actual yield always needs to be less than theoretical yield, because you're dealing with a percentage up here, the percent yield cannot be more than 100%. You can't make more than the perfect theoretical yield. One of the things to also note is that actual yields and percent yields correspond to real experiments. So theoretical yield, you can calculate. You can always calculate that yourself. You cannot just calculate an actual yield or a percent yield without having the other. You can use the equation. If you know one of those variables, you can figure out the other. But what you can't do is just determine both of them from nothingness. Theoretical yield you can, because you can do a stoichiometry problem. but the other two, they have to reflect reality. They either you did an experiment or in like a problem kind of context, one of them has to be given to you. Along those lines, let's look at a problem. In an aspirin preparation, 124.5 grams were produced. If the theoretical yield was 145.4 grams, what was the percent yield? Okay, so if we're looking at what do we want, it's percent yield, right? What was the percent yield? And this is, we don't want to waste it. Percent yield is an equation. A lot of world of stoichiometry has no equations, but this is the one equation in stoichiometry, so let's take advantage of it. So if we want percent yield, it's really, do we have the actual yield and the theoretical yield? So when we're looking for yields, we know that means mass of product. When you're told this is an aspirin preparation, that means you're making aspirin. So these masses that were produced, or these masses are going to be masses of the aspirin. That's the product you're trying to make. So you're given two different masses of aspirin. And so the question is, which one's theoretical and which one is going to be the actual yield? Aspirin preparation, 124.5 grams were produced. The theoretical yield was 145.4. What was the percent yield? All right, so whenever we see that word percent yield or that phrase percent yield, we want to recognize that there is an equation associated with it. So what that means is we can use that equation to help us figure out how to move forward. Percent yield is actual yield divided by theoretical yield times 100. Okay, so we want this, but the question is, do we have the other two values, right? Do I have actual yield and do I have theoretical yield? Because if I have those two, numbers for those two things, I can just plug those in and do the arithmetic to get percent yield. And so when we see this word yield, that needs to be a mass of product. So aspirin preparation means I'm trying to make aspirin. So all of these yields need to be masses of aspirin. Okay, so I would expect that these are mass, they would always be a mass of aspirin. And so I have two masses that are given right here. 124.5 grams were produced. So when we see that were produced, that means it reflects reality. Okay, so this actually happened. That means it's my actual yield. So my actual yield is going to be 124.5 grams of aspirin. And I'm told if the theoretical yield was 145.4, so that is explicitly telling you that it is the theoretical yield is 145.4. But you would, the language that you could certainly look for, like if it was possible or it was predicted that this could happen, because you'll note that doesn't reflect what actually happened, that reflects what could have happened or the potential. It was potentially possible, it was maybe possible, it could have made, any sort of kind of in theory ideas or only in thought, not in reality. Whereas anything that reflects reality is going to be your actual yield. So what that means is we can go ahead and plug all that stuff in. Percent yield is equal to actual yield divided by theoretical, whoa, oopsies, I meant to actually plug them in. Okay, so percent yield is, not just rewriting it, 124.5 grams of aspirin divided by 145.4 grams of aspirin times 100. So one quick thing that I want to note, in this reaction, you're only told one product, that it's aspirin, but most reactions have more than one product. So yield is just product mass. When you're calculating percent yield, you want to make sure that they are the same product that you're looking at. Those are both grams of aspirin, so they will both cancel out. 104.5 divided by the 145.4 times 100 is going to give you 85.63%. There are 4 sig figs on this. So 85.63% is your percent yield. And what that really means is of the possibility, right? Your possibility was to get the 145, you got 85% of it. So really that does imply that you could do better. There is room for improvement. And conversely, that also means you lost 15%. Because if you didn't get that product, what that means is that you wasted reactant. So you spent money on reactant and it did not lead to product, which can potentially be an issue. So this percent yield lets us kind of characterize how we did at a reaction. In that example, we did 85%. That isn't that great, right? That means you're losing 15%. And you know, if you're just trying out the reaction, then hey, 15% loss isn't that bad. But you know, say you're running a chemical plant, right? Plenty around here. You're running one of those. If you are putting in like literal tons of reactants, if you're losing 15%, if you're not making 15% product, that means you are wasting 15% of your reactions. That's going to start to add up to be a lot of money that you are losing. You better be making a product that is highly valuable. But at the same time, if you have a higher efficiency, you would just be making more money for the same cost. So when you're running chemical reactions in order to make product, you want to be at as close to 100% as possible. Living things are always at 100%. Your body right now is performing a huge number of chemical reactions. Every single one of them has to happen completely to completion, right? You have to get perfect conversion to product. Because, you know, one of the things is there's a lot, your body kind of does a lot of small reactions that add up to big changes. So if each time you lost, say, 5%, that quickly would add up to getting nothingness over the course of hundreds of reactions. Additionally, if you lift your arm, that needs to happen. It can't be, oh, I lifted my arm and it went 50% of the way, right? It needs to happen fully and completely. So all organisms have developed methods of performing chemical reactions at 100%. That's where enzymes come in, where the reactions are extremely controlled. They happen, they start when they need to happen, and they go, right? They don't just kind of 50% of the time it goes. Or, you know, you move your arm and you think you want to move your arm and 85% of the time it works. You know, it needs to be 100%. So having really high efficiency for chemical reactions is very important. And computing percent yield kind of lets us see, how did we do? So let's look at another example that kind of puts all of this percent yield in context. When 42 grams of silicon was reacted with an excess of chlorine, 202 grams of silicon tetrachloride was produced. What was the percent yield of this reaction? All right, what do we want? Percent yield. Okay, so because it's percent yield, we know that that's an equation. And so we really just need two other variables. We need our actual yield and we need our theoretical yield. Okay, so do we have those? So if it's yield, we're looking for a mass of product. The product in this case is going to be SiCl4, our silicon tetrachloride. And so actual yield, theoretical yield. Okay. So we are told 202 grams of silicon tetrachloride was produced. That language, was produced, means it actually happened. So that's an actual yield. That is an actual yield. That value we can then plug in as the top part right here, right? That tells us right away, boom, we've got our actual yield. Well, what about the theoretical yield? Well, in this case, there's no other mass of silicon tetrachloride. We're given a mass of silicon, but we can figure out the theoretical yield. It's in theory. You are never going to do an experiment and measure the theoretical yield. You're always going to have to figure it out in theory. And it comes from stoichiometry. So this reactant mass that we're given is going to allow us to calculate the theoretical yield, the maximum amount of product we could get. And this overall setup that you're told, this is how you would do a chemical reaction, right? You have an amount of reactant, your 42 grams of silicon, you do a reaction with a bunch of chlorine in this case, and you get some product. You got your 202 grams of SiCl4. Then you want to know, how did you do? Did you do a good job? Did you get as much product as you possibly could? Or is there room for improvement? And that's kind of the things that we want to think about, and we want to be able to improve how we're performing. So let's see how this works.
42 grams silicon was reacted with an excess of chlorine. 202 grams of silicon tetrachloride was produced. What was the percent yield? So again, percent yield gives us an equation to work through. In the world of stoichiometry, there's not a lot of equations except this one. And so we want to, whenever we can, we want to take advantage of that. Percent yield is going to be actual yield divided by theoretical yield times 100. And so if we want percent yield, we need to look for these two things, right? We need actual yield and theoretical yield. Yield means product, so I'm looking for mass of SiCl4. I want masses of silicon tetrachloride. Well, I'm given that explicitly. 202 grams of silicon tetrachloride was produced. So that is a yield because I only have one product, and this is the mass of that product. Okay? And so then the question is that actual or theoretical? So because we see that word was produced, that tells me it's actual yield. So 202 grams is going to be my actual yield. So then the question is, where's the theoretical yield? Well, no other yield is given in the problem, right? No other yield is given in the prompt, just 202 grams of silicon tetrachloride. The other mass I'm given is silicon. I have 42 grams of silicon, which we can see is a reactant, right? We're just dealing with a mass of reactant. And so the thing is, theoretical yields only exist in theory. And what that means is you can always calculate that out using stoichiometry. Every single result that we've gotten from stoichiometry up to now has been a theoretical yield for something, right? That is a theoretical yield for some reaction. And so if we want to figure out the theoretical yield, what we can do is we just get it from stoichiometry. So it's really common to have a situation like in this prompt where you need to calculate it yourself. And this is real life how you would do it, right? This is, I ran a reaction, I put in some amount of reactant, right? I ran a reaction, I put in 42 grams of starting mass, I did the reaction and I got some product, okay? And so then you want to know, how did you do, right? This is the general way in which we do chemistry. You don't necessarily know, you can figure out the theoretical yield, but it's never going to be like in the kind of setup of your reactions. This is what the theoretical yield is. You need to kind of you need to do that calculation yourself. So let's do that. We're going to calculate our theoretical yield. And so this is going to be a stoichiometry problem. 42.0 grams of silicon. I know in stoichiometry, the best first step is always use the molar mass to go to moles. I'm now in moles of silicon. I just looked up that molar mass on the periodic table. Now I want to go from moles of silicon to moles of my silicon tetrachloride. So I'm going to use my reaction coefficients. This is a balanced chemical equation, and I can see it's just 1-to-1. 1 mole SiCl4, 1 mole Si. So I've used my reaction coefficients. And then finally, in order to get it into mass, right, because I want to match this grams of silicon tetrachloride, 1 mole of SiCl4 is 169.89 grams SiCl4. So molar mass of silicon tetrachloride. It's worth noting here that I'm not showing calculations on how to come up with molar masses, because at this point in time, I expect that you know how to do that. So what we're going to be looking at now is, can you use those molar masses to do stoichiometry? So you'll note on the participations and stuff, I'm giving you those molar masses because I'm not going to expect you to be calculating those on your own at this point in time. I want to know, can you use them? I'm going to give you a bunch of molar masses. You don't need them all. Do you know how to use these tools? We've already looked at, can you calculate them? That was in chapter 3 and then on the last test. So from now on, I'm generally going to give you all the molar masses that you're going to need. But with that in mind, we need to do some calculations. So let's see. So the grams of SI cancels right there. Moles of SI, moles of SI, moles of SiCl4, moles of SiCl4. And so what we get out of this, when we put it all together, is 3 sig figs, 254 grams of SiCl4. And that is going to be my theoretical yield. Okay. And so then I wanted to, that's not quite what we wanted in the end. This is what you could have done. What we want to do is plug that back into percent yield. And so we find percent yield is going to be equal to the actual U, which that's one we were given. 202 grams of SiCl4 divided by 254 grams of SiCl4 times 100. Importantly, those cancel out. They are the same compound. And what we get from that is 79.5%. Overall, I'd say not that good, but you know, it's one of those things. It's a question of, where are you in this? Is this the first time you've ever run this experiment? Then hey, not too bad. Have you been doing this for years trying to get it perfect? Yeah, not very good. And so it's really kind of a question of that context. But this overall process is one that we can always do, or that, you know, we can start from this idea of, if you know, and this is really kind of the generic way in which we actually run real reactions. You know how much you start with, you can measure the mass of how much you end up with, then you want to kind of quantify how did you do by calculating percent yield. Because 202, that feels like a lot, right? Like I got a bunch of silicon tetrachloride. I only started with 42 grams of silicon, but the thing is, you could have done better. You could have done quite a bit better. You know, you lost about 20% of what you could have done. It's quite a lot of silicon that you're throwing away. Okay, another video done. Looking for any more questions on participation 615? I don't think there was one in this video, but maybe the next one. See you there.